Friends, welcome to the 6th lecture in module 3, where we are going to extend the studies on tubular joints based on experimental and numerical investigations. So, we say experimental studies and of course numerical as well on T joints. Let us focus on T joints in this lecture. This is lecture 6 on module 3, the online course on risk and reliability of offshore structures. In the last lecture we discussed about the general behavioral phenomena of a tubular joint irrespective of its geometry, maybe K, Y, T, etc. We also said there are various parameters which actually affects the behavior of tubular joint under the cyclic stress behavior. One can always use stress concentration factors obtained from the parametric equations to obtain or to determine the fatigue life of tubular joints, but there are many factors that influence the estimate of stress concentration parameters or factors in hotspot areas, because hotspot stresses are not only seen in the vicinity of saddle and crown, but also nearby the juncture, which can also improve the understanding of the behavior. So, we decided to pick up a specific case of a load study of a tubular joint. Before we look into the experimental setup and the definitions and derivations or the conclusion summary what we get from the investigations made by Rohit, one of our master student under the user oriented program of L&T sponsored program in Department of Ocean Engineering, it is very interesting that let us try to summarize what could be the reasons of failure of a tubular joint. So, based on the literature one can infer that tubular joint generally fails if any one of the condition, if any one of the following conditions are satisfied. Let us say stress in material, reaches elastic limit, stress in material reaches yield strength. First crack is detected, in the tension joint, maximum load carrying capacity of the joint is reached in compression. Which can cause large deformation. So, these are some of the important factors which will intuit the failure of a tubular joint as seen from Chandrasekharan and Bhattacharya. In specific terms, T joints under axial loads fail by two reasons. As stated by graph 1981. What are these two reasons: ovalization. Second, it could be punching shear. Now, one can also divide this explicitly by a specific value. For tubular connections or for tubular joints with B less than 0.3, failure generally occurs by punching shear. Which can be caused or results in punching in, which can result in punching in or pulling out of the plug, pulling out the plug from the side of the cord. For B exceeds 0.8, cord generally fails by collapse. So, for a geometric parameter B which lies between the range of 0.3 to 0.8, one should actually estimate the interaction of punching shear and the general cord collapse. So, for 0.3 to 0.8 range, one should actually study the interaction behavior between the punching shear and general cord collapse. That is what the literature advises. So, this will give me the failure pattern based on which I will be likely to estimate the fatigue life of the joint. So, therefore, it is necessary to know when my geometric parameter is between the range of 0.3 and 0.8, I should have to study the interaction between the punching shear failure and the general cord collapse. There is another critical issue which is very important in tubular joints. Please note that tubular joints generally fail in multiple modes. So, there is no guarantee that what mode of failure will prelude the other one. It fails in multiple modes. So, one has to examine this joint behavior very carefully using experimental investigations. So, such statements impose challenging nature in estimating the probability of failure. So, the challenges in estimating the probability of failure of the tubular joint could be the local failure of the cord. We have to check for this, the general collapse of the cord, further unzipping or progressive failure of the weld, and fracture and delaminating fatigue. So, these are some of the major challenges one need to understand before estimating the probability of failure of a tubular joint. Now, based on the finite element analysis using shell elements, various researchers has actually developed parametric equations to estimate the joint life in the reliability perspective rather than the design perspective. So, it is more in reliability perspective and not in design perspective. Please understand, this is a very important statement which we are making. Examples can be seen from the studies reported by Theomu and Durkin 1985, Kwong 1975, Raja Shankar et al. 2003. So, the parametric equations suggested by the researchers are essentially on the reliability perspective. Please understand this. Though people use them for estimating the fatigue life or estimating it as a design parameter, but essentially the purpose of this were not for designing the tubular joint, they are only to estimate the fatigue life in terms of reliability perspective. So, coming to the experimental and numerical investigations of the present study, T joints are fabricated and investigated under two combinations. One is the axial load and the other is out of plane bending. The geometric parameters of the tubular joints, especially T joints, are very important to really assess their behavior under these combinations. So, the geometric parameters of the T joint used in the study are as follows: beta ranging from 0.2 to 1, T ranging from 0.2 to 1, nu lying between 8 and 32, alpha between 4 and 40, theta between 0 and 90, 20 and 90, 20 and 90, and the gap which we call as tau is taken between 0.6 beta by sin theta to 1. Of course, these are guidelines given by APRP 2A 2000. based on which the specimens are fabricated and experimentally investigated. Kindly pay attention to the photograph shown on the screen now, which is a T joint fabricated for the study. You can see here the cord and the brace, which is at 90 degrees to each other, which is being investigated currently for the study. Kindly pay attention to the geometric details of the T joint, which has been used for the study. The diameter of the brace is 234.3 at this end, the diameter is about 114.3 at the connecting end, and the flange plate is about 234.3 millimeter. The brace is extended by 335 millimeters from the cord surface. Thickness of the brace is 6.02 millimeters. One can also see that the cord is having two flange plates of 12 mm. The cord length is about 1500 millimeters, whereas the brace length is about 335 millimeters. The cord diameter is about 168.3 millimeters against the brace diameter is 114.3. The thickness of the cord is about 7.1 millimeters, whereas it is about 6.02 for the brace, and so on and so forth. One can also see the bill of materials prepared for fabricating it, and one can see what is the total model in terms of kg, the weight of the model which has been used for the study. Welding of the joint is done as per APA recommendations. They are also tested for any defects using magnetic particle test. If you really wanted to apply an improvement factor on the fatigue performance of welded joints, there are many methods available. To use improvement factors on the fatigue performance. Of welded tubular joints. One can look for controlled burr grinding, if you are using a controlled burr grinding done on the welded surface of the weld toe, then one can always use the improvement factor on the fatigue performance. If you are done hammer peening, then also one can add the improvement factor. If you can also say using it as welded profile, then the performance factor is different, because as welded profile, if you are able to obtain a smooth concave profile which blends with the parent metal nicely, then one can also again use improvement factor for fatigue performance. But in the current study, no such special treatments are done on the weld surface. So that no improvement factor is actually foreseen in the given study. Kindly pay attention to the axial load setup which is being used for investigating the T joint under the axial load. The left hand side is actually the assembly which is housing the T joint, which is connected to the loading jack, which is then facing the reaction wall on the right side. The schematic view of this is shown on the right hand side picture, where the T joint is assembled between the box girders and the supporting frame, and the brace is now connected through the hydraulic jack to the resisting wall or the reaction wall, which is going to offer me the load through which the load will be transferred to the entire setup. Please pay attention to the photograph shown on the screen now, which shows me the experimental setup with various components. The test sample is what you see here from a different view. This is the reaction of the resisting wall. This is the box girder and the A frame. A frame is actually locked to the floor, so that the A frame does not allow the flange plates of the cord to get twisted when the loading is applied. The other view shows how the hydraulic jack is actually giving the force, axial force to the brace. This is a picture which shows clearly the LVDT located, which can also be seen in two different pictures. The test setup what you saw in the photograph is actually custom designed. We sincerely thank the structural engineering people of civil engineering department, the faculty and the staff of the structural engineering group of civil department of IIT Madras, who has dedicatedly prepared this test setup exclusively for ascertaining the requirements as suggested by myself and my student who can conduct the experiment on this. An existing reaction wall is used. The reaction wall has a capacity of about 200 tons. It is used to apply the load. The stiffened I section is placed between the loading jack and the reaction wall. This will ensure a smooth loading surface. A frame is used for fixing the edges of the cord member. Which is custom designed for this setup. The A frame is locked using a torque machine so that torque of course is locked to the ground using a torque machine, so that no moment at the base of the frame is created. To find the hot spot stresses in the vicinity of the weld, strained rosette is placed at 0, 45, 90 degree. They are used to measure the deflection. Please pay attention to the photograph shown on the screen now. The strained rosette with samples fixed on the sample is shown in the photograph. One can see here there are 3 strained rosettes at 0, 45 and 90 degrees, which are placed respectively on the sample to understand the strain at different directions, based on which the stress concentration on the hotspot stresses are going to be computed. LVDT, linear variable differential transformer, is used to measure the deformation or the displacement of the brace with respect to the cord. Strains are measured on the physical model using the strain gauge rosettes, as you just now saw in the photograph. The maximum principal stresses are given by, let us say, sigma 1, sigma 2, strain A and C by 2 of 1 plus 1 minus nu plus root of A minus C plus 2 BAC divided by twice of 1 plus nu where the strains A, B, C are respectively from the strain gauges at 0, 45, 90 degrees. Strain A and C twice of 1 minus nu. So, this is sigma 2, so minus root of A minus C square plus 2 BAC. Oh, this is 2 the whole square divided by twice of 1 plus. So, let us call equation number 1 and 2. So, sigma 1 and sigma 2 are the maximum and minimum principal stresses. Epsilon ABC are the strain values. Measured at 0, 45 and 90 degrees respectively. Capital E is the Young's modulus of the material and nu is the Poisson's ratio. During the conduct of experiment, extra stiffening is provided between the frames to actually avoid any unwanted damage to the frames as well as to the specimen. This is also required to ensure fixity conditions at both the ends, because the cord both ends should be fixed thoroughly and the brace should be able to apply the axial force from the reaction wall. So, to hold this cord thoroughly at a fixed boundary condition while the load is applied, which generally have a tendency that these cords or the brackets of the cords may get warped off, extra stiffeners are provided between the frames to ensure that unwanted damage to the frame or the loading frame does not occur as well as to the model. Interestingly, the stress concentration factor to obtain the hot spot stresses essentially depends also on various parameters of the cord and brace which has been chosen for the study. So, kindly pay attention to the details of parameters of T joint under the axial loading shown on the screen now. We have taken 3 specimens designated as T1, T2 and T3 as shown in the table. The dimensions of the cord with its diameter and thickness and the dimensions of the brace with its diameter and thickness is shown in the table, based on which the parameters beta, tau, nu and alpha are calculated, which is seen in the screen now. In addition to the experimental investigation, numerical analysis is also carried out on the T joint under the axial load to compare the behavior obtained from the experiments to really check which is superseding the other. Stress concentration factors are also obtained from the numerical analysis directly. If you look at the results of the numerical analysis, please pay attention to the figures shown on the screen now, which shows the axial loading condition and the hot spot stress points generated in terms of contour in the saddle and in the crown as shown in the picture here. Now, let us compare the results obtained from the experimental and then let us see what will be the parametric equation applicable for the specific case. Kindly pay attention to the table shown on the screen now, which is giving me the stress concentration factor parametric equation and the parametric validation used for the T joint under axial loading. If you look at the cord saddle and cord crown and the brace saddle and brace crown, based on the equations, the short cord connection is estimated and qualified as to be seen on the table now, based on which the parameters alpha, beta, nu, tau and theta as shown on the screen now in the table are estimated and the values for each one of them are listed. The validity is also shown as I explained earlier, and it is confirmed that these values do lie within the range of the study as recommended by international codes for a tube joint, for a T joint under axial loading. Now, to find the stress concentration factor experimentally, strain values measured from the strain rosette are converted to appropriate stress values. To compute the applied stress. The applied stress, which in this case is also called as nominal stress, is given by the applied load on the brace by the area of the brace resisting this load. Then the stress concentration factor can be simply said as the hot spot stress divided by the nominal stress. Let us call C question number 3. In order to understand the validations or variations on stress concentration factor values which influences the fatigue life estimate of the tubular joint T joint under the axial load, the fatigue assessment of the T joint is also done using SN curve approach. So, the fatigue assessment is also done using the conventional SN curve approach. It is only to understand the variations in stress concentration factor obtained experimentally. Interestingly, design SN curves for tubular joints in air with a chord wall thickness of 16 millimeter is given by a specific equation. Let us say the design SN curve with chord wall thickness of 16 millimeter for tubular joint in air is given by log 10n log 10 K1 minus m log 10 where equation number 4 where n is the predicted number of cycles to failure under the stress range S. K1 is a constant and m is the slope of the SN curve. So, the constant K1 for the welded joint for our specific case, that is log 10 K1 for S in megapascal is obtained in two cases. One is taken as 12.48 for m 3 for the number of cycles to failure is less than 10 power 7, is taken as 16.13 and the slope of the curve remains 5 for n greater than 10 power 7. Kindly pay attention to the allowable number of cycles for T joint for different stress concentration values as obtained from experimental and computed from the parametric equations for both the cord and the brace saddles. If you look at the cord saddle, the experimental and parametric values of the stress concentration factors are seen based on which n cycle is computed. For the brace saddle again, the experimental and parametric values, the stress concentration factors are worked out based on which n cycles are estimated. One can see from this table that the stress concentration factors obtained experimentally for both the cord saddle and the brace saddle for the T joint is lower compared to that obtained from the parametric equations, as a result of which the stress cycles or the number of cycles to failure in the stress range is higher experimentally compared to parametric equation for both cases of cord saddle and brace saddle as seen from the table. So, from the above comparison, one can easily observe that the fatigue life of the joint significantly increases because there is a significant reduction in the stress concentration factor which has been obtained experimentally. When you compare this with another parametric equation, uncertainties with respect to life prediction of offshore structures can easily be seen through this particular comparison. One is also interested in estimating the fatigue life of the T joint under axial loading. Please pay attention to the tabular values given on the screen now. For the axial loading, both for the cord and for the brace, comparing experimental and parametric. So, these values practically are taken from the previous table of the n cycles. For the values computed, n cycles based on the stress concentration factor determined experimentally or from parametric equation, the permissible n per year is taken as 500,000 for this specific kind of joint under axial loading, then based on which the fatigue life in terms of number of years is estimated. One can see here very easily that for the cord, the fatigue life is compared to be 31.67 against 24.62, which is computed or which is recommended from the parametric equation. Similarly, for the brace, experimental studies show that the fatigue life is very high compared to the parametric estimates. So, if we consider 500,000 cycles per year as a base, increase in life of the joint is considered to be 24.62 years, which is increased now to 31.68 years, which is fairly about 40% increase. So, the experimental studies conducted on T joint under axial loading and out of plane bending shows very clearly that the fatigue life estimates done based on experimental investigations are higher compared to the parametric equations. For all the 3 joints T1, T2 and T3 considered for the study, the failure observed is actually a punching failure mode with the weld intact. As I said in the beginning, ovalization of cord is observed till the cord member yielded, after which plastic deformation occurred near the weld area, which resulted in sudden punching of the joint. So, the failure phenomena, or let us say the failure pattern or the failure behavior, is actually ovalization of the cord till the cord member yielded, after which plastic deformation occurred. Near the weld area. Which resulted in sudden punching of the joint. So, one can see the path of failure which has been traced based upon the experimental investigations and observations. It is also plotted interestingly, and the figure can show this, which shows both in punching mode and shear mode there is a bulging of the joint indicating there is a plastic hinge formation. If you pay attention to the photograph shown on the failed T joint in punching shear, one can see that experimentally and numerically both showed the bulging of the joint. It can be seen from the figures very easily that influence of the axial load on the cord is extended beyond the brace diameter region. Please pay attention to the figure shown. There has been influence of this failure beyond the base region, which is actually shown both experimentally, there is a bulging here, there is a bulging here as well. This is an important information to account for uncertainties in reliability parameters. The region of influence also plotted. The maximum hotspot stresses are observed at the saddle point and minimum at the crown point of the weld, as can be seen from the failed T joint showing bulging of the joint again. So, one can see here that the saddle and the crown points showed bulging, as you see, which is also verified from the numerical investigation. Please pay attention to the picture shown on the screen now, which shows the region of influence of the T joint under axial load failure. It is not only the brace region, but beyond the brace region even the adjacent circumferential area is also affected. So, these are the reasons why the stress concentration factor or the fatigue life estimated from the experimental investigations are higher compared to that of the parametric equations. So, one can see that the stress concentration factors computed from the experimental investigations are lesser in comparison to the parametric equations, indicating there is a necessity for reliability estimates through experimental investigations. Fatigue life of the T joint under axial load increases significantly by about 40% when you examine them experimentally compared to that of the parametric equations, which increase from 24.62 of the cord to that of 31.68 years. So, friends, this application example showed interestingly how uncertainties in estimating the stress concentration factor, which is one of the pivotal issue in estimating the fatigue life of the T joint or the tubular joints in general, are very importantly highlighted. One can understand physically the factors which are very important that are contributing for this kind of enhanced fatigue life assessments. So, even if you are using the parametric equations which give me a conservative estimate of the fatigue life, but one should really know why there is a difference between the fatigue life estimated from the experimental studies in comparison to that of parametric equations, which is one of the important issue in understanding the reliability of the behavior of tubular joints. So, as I said in the beginning, the focus is on reliability perspective, not on design perspective. So, it is important to know that uncertainties do exist in estimating the fatigue life or reliability estimates of tubular joints, and as an example illustrated through this presentation, one can easily appreciate that these factors can contribute significantly to the understanding of the failure behavior, because we also discussed about the so called path of failure based on which actually a T joint under axial force fails from the experimental investigations. So, this study as an example could be very valuable for reliability estimates. We thank the structural engineering group of civil department of IIT Madras and L&T, which sponsored this particular study in financial aspects through the user oriented program running at IIT Madras in the Department of Ocean Engineering by L&T. Thank you very much and bye.